All right, let's just jump right in. We all have memories, right? Your first bike ride, the melody of a song, the face of someone you love. But have you ever stopped and wondered, where is that memory? Not just as a thought, but as a physical thing inside your brain. Today, we're basically detectives, on the hunt for the physical traces of memory, trying to unlock the brain's code.
I mean, this is the core mystery, isn't it? An experience can be over in a flash, but the memory of it can last an entire lifetime. So how does the brain do that? How does it capture something so fleeting and store it away for decades? That's the huge question we're unpacking right now.
You know, in any great investigation, you need a prime suspect. And for neuroscientists trying to solve this mystery of memory, they've got one. Its name is the Synaptic Plasticity and Memory Hypothesis. Yep, it's a mouthful, but it's the leading theory, the top suspect, for how our brains physically record information.
So what in the world is synaptic plasticity? Well, simply put, it's the brain's power to change the strength of the connections between its neurons. The paths in a forest analogy you see here is honestly perfect. Imagine your brain's connections are all trails through a dense forest. Every time you recall a memory or practice a skill, you're walking down one of those trails. The more you use it, the wider and clearer that path becomes. That, right there, is plasticity at work.
Now, this process is a two-way street. On one side, you've got LTP, which stands for long-term potentiation. This is the strengthening part. That's our well-trodden path. But on the flip side, you have LTD, or long-term depression. This is what happens when a connection gets weaker from disuse, kind of like an old path that gets all overgrown. One helps you remember, the other helps you forget. And believe it or not, you absolutely need both for a healthy brain.
Okay, but having a good theory, a good suspect, isn't enough. We need proof, solid evidence. So to get it, scientists have developed this incredible checklist. 5 critical clues they need to find to prove that this hypothesis is the real deal. Let's walk through that list.
And this checklist really shows you the scientific rigor here. First, detection. Can you actually see plasticity happening at the exact moment a memory is being formed? Second, mimicry. Does the kind of plasticity match the kind of memory? Then, location. Does it all go down in the right part of the brain at the right time? Number 4, blockade is a huge one. If you actually stop plasticity from happening, does the memory fail to form? And finally, the ultimate test, induction. Can you go in, artificially create plasticity, and literally build a memory from scratch?
So, with our checklist in hand, where do we even start looking for this evidence? Well, the investigation takes us deep inside the brain, to the specific hubs that are responsible for all the different kinds of memories we have.
And here's the really good news for our hypothesis. The evidence is absolutely piling up. Scientists are using these unbelievable new techniques to actually record the electrical chatter between neurons and even watch physical changes happen in real time. They have confirmed this isn't just a theory, it's a real physical process happening in the exact brain regions we'd expect.
This table breaks it down so well. You look in the hippocampus, which is basically in charge of your life story and your sense of direction, and you see tons of LTP, that strengthening process. Then you go to the amygdala, the emotion center, and bam, the plasticity there is tied directly to emotional memories. And all across the cortex, which handles our higher thinking, we find all kinds of plasticity at work. So that location clue on our checklist, we can definitely put a big check mark next to it.
So, we've followed the clues, we've examined the evidence from all over the brain. I think it's time. It's time to deliver the verdict. Is synaptic plasticity the one and only mechanism behind memory? And this is where the plot twists. The verdict is split. Is plasticity necessary for memory? The answer is a resounding yes. We have tons of evidence showing that if you block it, you block memory formation, period. But is it sufficient? In other words, is it the only thing you need? On that, the evidence says, not yet proven. We still haven't fully solved that 5th and final clue on our checklist, artificially creating a memory. And that's really the crucial point here. We know that plasticity is a required ingredient. It's like flour in a cake. You absolutely cannot make a memory cake without it. But it might not be the entire recipe. You can't bake a whole cake just by adding flour, right? There have to be other ingredients, other steps. And that's the next great mystery for scientists to solve.
And that, of course, is what leads us to the next frontier in this research. The focus is shifting from looking at single connections to understanding how vast networks of neurons all work together. Scientists are building these incredible new tools to manipulate very specific circuits in the brain, all in the quest to finally solve that lingering question of sufficiency. Which brings us to a final, kind of mind-bending thought. All this science is pushing us toward a future where we might not just read memories, but actually write them. So, if we finally crack the code, if we gain the power to create a specific memory in a person's brain, the question is no longer can we, but should we? And that is definitely something to think about.